This week we're focusing on the 7th grades, particularly in expressions and equations. This week we're going to use algebra tiles and some number lines to help us solve equations and inequalities. So let's get started. These are the list of pieces within the cluster for the equations and expressions. So in our introduction to algebra tiles, for each pair of expressions, state whether they are always, sometimes equal, or never equal. Explain how you know. X can be any rational number that we can think of. So 1x and x and so forth. So to get to my algebra tiles, the ones that I'm going to particularly use within our class here, I'm going to click manipulatives, move this over for you. And I'm going to click on the second one, the algebra tiles and base 10 pieces. So it comes up in this screen. I really like these particular algebra tiles by clicking here, and then we have our list. So we have the x values, and we're not going to quite get to the x squareds yet, but we also have a y tile, an x times a y, and then the unit tile. Note that if I double click an item, it can rotate for us further. If we click one time, we get a negative value. So our first one is just x and 1x. By having 1 out here, that implies that there is a 1 in front of x, even though we don't see the number. So x and 1x are always the same. Then I have x plus x plus x plus x. I'm just going to move these closer together here. All right, so x plus x plus x plus x. So I've got 4 x's, which is always the same as 4x. Okay. Then we have 3x plus 2. 3x plus 2. Is that the same as 3x? Never. These are never the same. And 3x and x3. Well, that would be part of the commutative property since we can multiply in any direction. So x times 3 or 3x is always the same. And then I have 3x, so 1, 2, 3x and 6. 1, 2, 3, 4, 5, 6. This is sometimes true because when I put in 2 for the x value, I could get 6. If I put 2, 4, 6, these would be the same. But if I did 1 in the x value, 3 times 1 would be 1, 2, 3, so that would not be the same. So this last one is the only one that is sometimes true. All right, let's go back to our lesson here. Line it up for us. Okay. Equivalent expressions will always have the same value regardless of the types of numbers or variables included. We can determine if expressions are equivalent by substituting numerical values for the variables. We can use properties of operations to transform one expression into the other. Choose the expression or expressions that is or are equivalent to the expression 3 times the quantity x minus 6 using algebra tiles. Our original equation or expression is 3 times the quantity of x minus 6. So we need 3 of x minus 6's. So this would be considered x plus 6. So I'm just going to turn all of these negative so that they become x minus 6. And I need 3 copies of this. So we're using that same area idea that we've used since elementary school to help build these for us, except now we're using variables and not just numbers. So along this left side, we can see there's 1, 2, 3, and along the top I have x minus 6. So is that the same as 3x? Here's 3x. Is that the same as 3x minus 6? There's 1, 2, 3 negatives. All right, 6 negatives. So although they both have the 3 x's, our individual numbers are short, so A is not appropriate. Is this the same as x minus 6 times 3? Well, absolutely, it's the same. We want 3 copies of x minus 6, except it's just in a different order. So we could easily rewrite this by flipping these around, and maybe instead we'll line them up this way. But we're still going to get the same result if I were to add more of them down here. So B is good. Is this the same as 3x minus 18? Well, if I were to count all my pieces, here's 1, 2, 3x, 3, 6, 9, 12, 15, negative 18. C is correct. Is this the same as x minus 6 plus x minus 6 plus x minus 6? Well, here's x minus 6 plus x minus 6 plus x minus 6. So the only true answers are B, C, and D. A is the only one that did not work for us. If we multiply x over 2 plus 3 copies of 1/4 by 4, we get 2x plus 3. Is 2x plus 3 an equivalent equation if we go backwards to x over 2 plus 3 copies of 1/4? Let's see if they are by plugging in the numbers. We know that if we plug in a number, it should work for any number that's chosen. So let's choose 1. When I plug in 1 for x, we get 2 times 1 plus 3. And 2 plus 3 is 5. So let's then plug in 1 for the x value with the fractional one. So we'd have 1/2 plus 3/4. We know that is the same as 2/4 plus 3/4, so 5/4 altogether. Notice they're not the same, so they are not equivalent. All right, write an expression for the sequence of operations. Add 3 to x. Then subtract that result from 1. So whatever that result is, we want to take 1 minus whatever that is. Then we're going to double what we have. Add 3 to x. So far we're starting off at the same. Double what we have. Then subtract 1 from this result. So although they sound the same, they are not the same. So be careful with wording. Be careful where things go. In these expressions, x can be any rational number. Find pairs of expressions that are equivalent and show how you know. I know that you know how to use the distributive property, and I'm going to show you some things that may or may not be comfortable for you. So be patient as we go through these. It's not a traditional way that we have seen or you may have seen in the past, but it is a way that 7th graders are reasoning, and so it's important that we know how to reason with them and show them how to reason differently than just straight algorithms. So I'm going to start with the top field, see if I can make these be the same. So I start with 3 5/10 minus 4x. Well, we know that we can rewrite it as an addition problem. So 3 5/10 plus a negative 4x. Then I can use our properties, our associative properties, and rewrite this as negative 4x plus 3 5/10. So those two are equivalent. And we can check by plugging in a number. So let's say I plug in 5 for x, so 3 5/10 minus 4 times 5 is 3 5/10 minus 20, which is negative 16 5/10. Similarly, negative 4 times 5 plus 3 5/10 gives us negative 20 plus 3 5/10, so negative 16 5/10. So they are equivalent. Let's try 6x and 2x minus 1 plus x plus 3. So I'm going to take 6x and I'm going to rewrite it as 2 plus 4 times x, because I know 2 plus 4 is 6. Okay, and then I'm going to separate them using the distributive property, giving me 2x plus 4x. And then I'm going to add 1 and subtract 1 here. I'm going to add 1 and subtract 1 because plus 1 and minus 1 is the same as 0. So we're adding in a 0, which does not change our overall expression. Then I'm simply going to rewrite them. So 2x minus 1, 4x plus 1, so that I can start to develop what that second equation might look like. So then what I did is I took 2x minus 1 and grouped them together. And then what I did, so I grouped these two together, and then I rewrote 4x into an x and 3x, because x plus 3x is 4x. And I rewrote 1 using 3 minus 2. So now I get this part to match this piece up here. However, we have these leftovers of 3x minus 2. So those two are not going to work. Let's try 6x and 5 halves x plus 7 halves. So 6x we know is the same as 12 over 2x. So manipulation a little bit. I can rewrite 12 halves as 5 1/2 plus 7 1/2 x, which means then that I can separate them using the distributive property. So 5 halves x plus 7 halves x. So those two are the same. And we can check using our numbers if you're uncomfortable. So if let's say 1, so 6 times 1 is 6, and if I did 1 for each one here, I'd end up with 5 halves plus 7 halves, which is 12 halves, or the same as 6, so they're equivalent. Let's try 1/3 times 8x. Is that the same as 8/3 x? So 1/3 times 8x, I can rewrite this using the commutative property. So 1/3 times 8, which is the same as 8/3 x. So these are equivalent. Let's try 2 times 2x plus 1 to equal 2 plus 4x. So using our properties, if I have 2 copies of 2x plus 1, that's the same as 2x plus 1 plus 2x plus 1. If I rearrange them and combine them together, that gives me 4x plus 2, or 2 plus 4x if I rewrote it. Let's see if I can't get those to match somehow. So let's start off with 4x plus 3 minus x plus 1. So I'll distribute the negative piece, giving me negative x, negative 1. I can rewrite them combining my x's and my digits together. So 4 minus x plus 3 minus 1 gives me 3x plus 2. Let's do the similar technique to the 2x minus 1 plus x plus 3. Rearranging them, we get 2x plus x minus 1 plus 3, so 3x plus 2. So these two are equivalent together.
We have seen that the same expression can be written in different but equivalent forms. Let's rewrite the following expression so that it is in simplest form. Show using algebra tiles. 2x plus 3x. Now this might seem mundane to us, but for someone just starting out, showing that they are the same is important. So if we have 2x and we add 3 more x, I see that all together I have 1, 2, 3, 4, 5 x's. So this is equal to 5x. Like terms are terms that contain the same variable and exponent, just like 2x and 3x, y and 2y, 4 and 6. Non-like terms would be something like 2x and y. If we look at 2x and we bring out y, these are not the same, so we cannot combine them together. Rewrite the following expressions so that it is in simplest form. Show using algebra tiles. Okay, so our first one is negative 3x. So I'm going to put up negative 3x here. And then it's plus 2. So plus 2. Okay. Minus 4x. So 1, 2, 3. We need another one. 4. And minus 6. 1, 2. We'll just put them next to here. 1, 2, 3, 4, 5, and 6. Okay, so we can combine all of these together to give us a total of 1, 2, 3, 4, 5, 6, negative 7x. I see that I've created two different groups of 0, so then I just need to bring down negative 4. So our final answer for this one is negative 7x minus 6. Okay, so our next one is 3x. So we're just going to start over. 3x minus 2 plus 1 minus 5x. 4, we need another negative x. Minus 5x minus 7. 1, 2, 3, 4, 5, 6, 7. Plus x, so plus a regular x. So I see that I'm going to be able to cancel out some and make zeros of x's. So I'm just going to do that now to get rid of them, pair them off here. I see I have one group, oops, and I have another one over here. So these pair off. So it looks like all we have left is negative 1x minus 1, 2, 3, 4, 5, 6, 7, 8. So this is equal to negative 1x minus 8, or negative x minus 8. Now this next one here, negative 2x plus 1 and 5/10 y minus 4x minus 6 minus 4y plus x plus 10 and 5/10 x, or 10 and 5/10. We have some decimals, and that's kind of where the algebra tiles start failing us. We don't have decimal forms of them. So at this point, after you've done many different examples with whole numbers, students should be able to see that we can group some of the common terms together, such as negative 2x minus 4x plus x. So negative 2 minus 4 will give us negative 6, plus 1 should give us negative 5x. Then let's look at our y's. I have 1 and 5/10 y minus 4y gives us a positive, or a plus a negative 2 and 5/10 y. And then finally, we can combine our whole number pieces or our numbers that are by themselves. So negative 6 plus 10 and 5/10 gives us a positive 4.5, or 4 and 5/10. Simplify the following expression by combining like terms. So here we notice that the 7 is on the outside, so we need to distribute that 7 first. So I'm going to distribute 7 to the negative 1/10 and x and to the 5/10 y, as you can see, which then means I can multiply my numbers together, giving me negative 7/10 x plus 3 and 5/10 y, and I just kind of tack on the remaining. I then see that I've got some x's together that we can combine together. So negative 7/10 x plus 1x gives us 3/10 x. And when we look at our y's, I have 3 and 5/10 y minus 5/10 y gives me a positive 3y. Ashley asked her friend Abby a riddle. Abby decided to use a tape diagram to solve this, and she decides that Ashley's number is 5. What might her diagram look like? How can we check her answer? If I take a number, multiply it by 3, and add 2, then the result is 17. So using a tape diagram is another way versus algebra tiles, but equally as effective, especially since it can work with decimals and fractions. So here's a number. It says if I take a number, multiply it by 3, so 3n's, and then add 2, this result altogether is 17. So our equation is 3n plus 2 is 17. If I plug in 5, because Ashley says the number is 5, we get 15 plus 2 equals 17. Jason wants to buy a video game console and 2 games that are the same price. The store is selling the bundle with 2 games and the console for $170. The game console by itself costs $120. Represent the situation with an equation where G is the price of one video game. How much does each game cost by itself? So again, it wouldn't be logical to use algebra tiles because 120 and 170 is fairly large. So we know that a game console plus 2 video games altogether is $170. We also know that the game console is $120 plus the 2 video games, which we represent with G, must equal 170. So I have the tape diagram here. So I have 2G plus 120, all of it together must be $170. Well, I see if I cut a line down and put the variables on one side and the numbers on the other, if I were to subtract 120 from both sides, that kind of knocks it off and I can just look at a portion of the tape diagram. So algebraically, I have 120 plus 2G minus 120 equals 170 minus 120. So 2G is equal to 50. Well, I can split that right down the middle. So if I were to divide it in half, each game, therefore, must be $25. And if we plug it back into the original equation that we discovered, 120 plus 2 times 25 certainly is 170. So a solution to an equation can be found by creating a series of equivalent equations using the same operation on both sides. So notice when we were figuring this out, we subtracted 120 from both sides, and when we were about ready to get G by itself, right here, we divided both sides by 2. Solve the following in 3 ways. 2n minus 5 is 23. So let's use the tape diagram first. 2n equals, must be something minus 5, so 23 minus 5. Well, what we can do then is add 5 to both sides so that n equals 28. Dividing it down the middle, n equals 14. Let's use operations on both sides algebraically. So we add 5 to both sides, so 2n equals 28. Divide each side by 2, n equals 14. So let's use algebra tiles. All right, so I've kind of got it set up for us here. For my background, I chose the equation mat, completely your choice if you want to use it or not. I just thought it'd help us kind of keep things separate. So I have 2n or 2x minus 5 equals 23 over here. So what I need to do now is get our x's here by itself. So to do that, I need to add in a series of zeros here, right? So 1, 2, 3, 4, 5. And what we do to one side, we have to balance out the other side. 1, 2, 3, 4, and 5. So now I've created a bunch of zeros. So all of these now get to disappear. Okay, and now I'm left with, and I'm just going to turn them on their sides, I'm left with 2x equals 28. So if I were to split these up, there would be 14 that belong to this x and 14 which belong to this x. So x equals 14.
Solve for the value of x by using the same operation on both sides. So another reason why I also like using these strips here is because we can show fractions more easily. Algebra tiles are great, again, with whole numbers, but not so great when we have fractions or decimals. So we have 1/3 of an x plus 7 is 10. So notice that this part here represents 1/3 of the whole value of x, which is why it's only shaded 1/3 of it. But then this whole piece must be 10. Then what we can do is subtract 7 from both sides. So if we were to take this bar here and split it down and subtract 7 from both pieces, we end up with 1/3 of x is 3 equals 3. Okay, so then if we know that this part is 3, then each one of the remaining ones also must be 3. So therefore, 3 times 1/3 of an x equals 3 times 3, which is 9. Solve for the value of x by using the same operation on both sides. So when I look at negative 1/2 x plus 4 copies of 1/5 equals negative 5 copies of 1/6, I can look at my denominators and see that 30 is the common denominator. So we're going to be efficient and solve the equation using the least common denominator amongst all of our fractions. So I will multiply everything by 30, which gives me negative 30 halves x plus 1/25 equals negative 156. And you can notice that each one of those can evenly be divided, giving me negative 15x plus 24 is equal to negative 25. So now we have to use the same operation. So we need to get that x by itself. So first we're going to subtract 24 from both sides, giving me negative 15x equal to negative 49. We then need to divide both sides by negative 15. So x is equal to 49/15. Is there a best way to illustrate why 3 times 5 plus 2 is equal to 3 times 5 plus 3 times 2? Well, on the left-hand side, looks like this particular student just wrote 5 plus 2 3 times. And then they rearranged them to be 5 plus 5 plus 5 plus 2 plus 2 plus 2, which is the same as 3 copies of 5 plus 3 copies of 2. Whereas this student did 3 by 5 plus 2 and broke it down. We have 3 copies. We can keep on breaking them individually, so we have 15 plus 6. The neighbor decided to buy cell phones for her family of 4. Each cell phone plan costs 10 cents per text message plus a $20 monthly fee. Each family member is allotted the same number of texts per month. If T represents the number of texts per family member each month, write an expression that represents the total cost for the family of 4. Use your expression to predict how much the neighbor will pay, or the neighbor's bill will be if everyone in her family sends 35 texts per month. So we know that it's 10 cents per text plus a $20 fee. So this could be our expression. But there are 4 family members, so we would need to multiply all of that by 4 so that every member in the family is counted. We can then use the distributive property to share the 4 with the 10 cents per text message and the $20 monthly fee, giving us 40 hundredths T plus 80. So let's use our expression to predict if we were to send 35 texts per month. So we will replace the text message piece with 35. 40 cents times 35 messages is 14, plus 80 is 94. An area model is given below. Select the expressions that could be written using the diagram. So I see I have 1, 2, 3, 4 y's and 1, 2, 3, 4, 5, 6, 7, 8 x's. So 4 y's plus 8x would be appropriate. Here's 4y, but then it has plus 2x, so it's not counting these 6, so B is not correct. 4 times y plus x. Well, we do have 1, 2, 3, 4 groups here, but each group is y plus 2x, not just y plus x, so C is not okay. Further, 4y times 2x. Yes, we have the 4y, but there is more than 2x across the top, so D is not appropriate. Letter E would work because we have 4 groups of y plus 2x. And F is y plus 2x plus y plus 2x plus y plus 2x plus y plus 2x. So that, of course, will work as well. So A, E, and F will all work. Solve the following equation using the distributive property. So 3 times the quantity 3x plus 2 is 24. So we need to share and distribute the 3 with each piece, giving us 9x plus 6 equals 24. Now using the same operations on both sides, we will subtract 6 from both sides, giving us 9x equals 18. Dividing each side by 9, not by 2, gives us x equals 2. Let's verify this using algebra tiles. Here are algebra tiles. I have set up 3 copies of 3x plus 2, so I have 3 of those copies, is equal to 5, 10, 15, 20, 24. So the first thing we would need to do is use the distributive property, but there's not much to distribute here because I already have it all laid out. So then what we need to do is we need to subtract 6 from both sides so that we can get these into copies of 0. So I'll add 1, 2, 3, 4, 5, 6. So by adding copies of 6, we know that these all here will just end up canceling out to be 0. And I can do the same here. 1, 2, 1, 2, 1, 1. Okay, now we still have 9x and we have 5, 10, 15, 16, 17, 18. Oh, I must have taken one too many away. No, 18 is right. 5, 10, 15, 16, 17, 18. Okay, so now let's see if we have these 9, how can I evenly divide up those 18 so that each x has the same amount of units? So I'll just start lining them up here. Kind of try to make them even. So it looks like each x value is equal to 2. So each x value equals 2. The perimeter of the larger square is 84 units. What is the perimeter of the smaller square? We know that perimeter is the same as adding all of our sides together. And we know that it has to equal 84. So 2x minus 1 plus 2x minus 1, etc. Knowing that there are 4 copies of the same thing, we can use the distributive property. After distributing the 4, we end up with 8x minus 4 is equal to 84. Using the same operation, we will add 4 to both sides, giving us 8x equals 88. Dividing both sides,
we see that x is equal to 11. Now we can identify the perimeter of the smaller square, knowing that the value of the smaller square is adding up all their sides, so x plus x plus x plus x, or there are 4 x's. Substituting in 11 for x, we get 4 times 11, which is 44 units. Arithmetic and algebraic approaches to solving problems are related, and both approaches can be written as equations. So Diego, Robbie, and Omar made flashcards for 60 science words. Robbie made 5/6 as many as Diego, and Omar made 4/5 as many as Robbie. How many cards did each person make? So let's start with Diego, Robbie, and Omar. So Diego made 5 out of 6. Okay, so Robbie made 5/6 as many as Diego. Omar made 4/5 as many as Robbie. So Diego has 1, 2, 3, 4, 5, 6. Robbie has 1, 2, 3, 4 fifths, and Omar has 1, 2, 3, 4. So it kind of builds this little tape diagram. And altogether they had 60. So if we're thinking arithmetically, Diego had 6, 1, 2, 3, 4, 5, 6 altogether. Robbie had 1, 2, 3, 4, 5, and Omar had 1, 2, 3, 4. So altogether they had 15. So if I take the 60 and divide it by the 15 cards, each one represents 4. So then Diego has 4 times 6, so each one of these blocks represents 4. So 4 times 6 is 24, 4 times 5 is 20, and 4 times 4 is 16. We could do this algebraically as well. If we were to let C represent the number of cards they have, we would have 6 cards plus 5 cards plus 4 cards must be a total of 60. Combining like terms, 15 cards equals 60. Dividing each side by 15, each one represents 4. So notice that whether we do arithmetic or algebraic, we are still adding and we are still dividing. Use a number line to model and solve the following. So I have n over 3 plus 2 is greater than 0. So right now we have an open dot because we have a greater than or less than symbol. And currently it's greater than 0, so we want things that are bigger than. So then our next step would be to subtract 2. So I'm going to move my dot to the left 2 so that we subtract 2. Now we're at -2. So n over 3 is greater than -2. But to get n by itself, we know we need to multiply both sides by 3. So if I multiply -2 by 3, we get to -6, but we're still moving in that direction. So n is greater than -6. Use a number line to model and solve the following. 1/2 of x plus 3 is less than or equal to, or -4 is less than or equal to 7. So this time our dot is filled in because it's less than or equal to, and less than is traveling left on our number line. We would want to add 4 to both sides. So from 7, moving it 4 units to the right because we're adding 4, 7, 8, 9, 10, 11. After that, we would want to multiply both sides by 2 so that we can get rid of the half. So 11 times 2 brings us to 22. And after that, we want to subtract 3 from both sides so that we get our x by itself. So 22, 21, 20, 19, and we're still facing the left-hand side there. And just to work through it algebraically here, so the first thing we did was we added 4 to both sides, giving us 1/2 times x plus 3 is less than or equal to 11. We then multiplied both sides by 2, so then we were left with x plus 3 is less than or equal to 22. Subtract 3 from both sides, so x is less than or equal to 19. There may be infinitely many numbers that satisfy an inequality,
which can all be shown using the number line. Solve and graph the inequality. I'm going to multiply by its least common denominator between 2, 4, and 1. So when I multiply everything by 4, even that 5 gets multiplied by 4, even though it doesn't have a fraction. Gives us 60 halves is greater than or equal to 4d over 4 minus 20. I can actually divide them through to get whole numbers. So 30 is greater than or equal to d minus 20. We need to get d by itself, so we're going to add 20 to both sides. So 50 is greater than or equal to d. Because we have a greater than or equal to sign, we will have a solid dot at 50. Now we need to determine which way our arrow will go. So I like to pick a point like 0. Is 50 greater than or equal to 0? True. Is 60 greater than or equal to 0? That's false. So our arrow needs to go left. It needs to be where all the true values are.
There may be infinitely many numbers that satisfy an inequality, which can all be shown on a number line. We're going to solve and graph the inequality. 6 times the quantity of 7 minus 2p is greater than 12. We'll first need to distribute the 6 through to the 7 and the negative 2, which is still greater than 12. When we multiply, we have 42 minus 12p. Our goal is to ultimately get p by itself, so we'll have to subtract 42 from both sides. When I subtract 42 from both sides, I have negative 12p is greater than negative 30. To divide, to get p by itself, we'll have negative 12p divided by negative 12 is greater than negative 30 divided by negative 12. Notice that we're dividing by a negative. This will ultimately change and flip the sign of our inequality. So because I'm dividing by a negative, I'm going to flip my inequality from greater than to less than. And 30 divided by 12 is 2.5. On our number line, I can place 2.5 using an open circle because we have less than, and we want values that are less than 2.5, which means that our arrow needs to point to the left. Jerry has $100 in the bank and deposits $18 per month. Ashley has $145 in the bank and deposits $15 per month. How many months will Ashley have a larger bank account than Jerry? Let's write and solve an inequality for the situation and then graph on a number line. On the left-hand side, I'm going to have what Jerry has in his account, $100 plus $18 per month. So I'm going to let X represent the amount of months. We want Ashley to have the bigger balance. So Jerry's value is less than Ashley's value, or Ashley is greater than Jerry's value. Ashley will be on the right-hand side with $145 plus $15 per month, where X is still representing the number of months. Let's just see what X is worth. We'll first start by subtracting 100 from both sides, giving me 18x is less than 45 plus 15x. Let's combine our x's by subtracting 15x from both sides. This then gives us 3x less than 45. We'll divide each side by 3 so that x is less than 15. So the number of months has to be less than 15 to represent the number of months which Ashley will have a larger bank account. So she will have the larger bank account for up to 14 months and some odd days because we don't have the equal to sign, so it has to be less than 15. So we will put our marker at 15 with an open circle, and any value below 15 will represent the amount of money that Ashley will have in her account that is larger than Jerry.